So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be proceeding in our playlist that is Advanced Calculus Explored. And so far, we have done the differential calculus, right? Second one is integral calculus. And the third one is your Feynman's trick. So far we are done with these things, right? Actually, these things are the chapters which we have successfully did, and now we are just going to have this fourth chapter, which is sums of simple series. So basically this is your fourth chapter and we have sums of simple series. So basically this chapter is consisting of some basic sums, right? Like so far we were like talking about calculus, right? But now onwards we would be proceeding in some sums, which is like, yeah, series, right? So yeah, it's kind of important because if you are a daily viewer of my channel, so you might have noticed that a lot of my videos, oh wait a second, my spelling is kind of wrong here, videos were are on sums, like they consist of sums and like series somewhere in those videos. So for that case we need to have a better knowledge about these things. So though it's not a difficult chapter because we are just going to introduce it in front of you, but yeah, of like for the next some chapters we would be just learning sums, right? So let's just get back to the video, let's just get back to the chapter, right? Okay, so we have introduction. In this chapter we will explore, wait a second, I think I should use this port laser instead of line laser. Explore the evaluation of simple series. So it's simple, right? So it doesn't mean that it's that much simple, but yeah, it's kind of simple, that much, it's not that difficult, right? Okay, though we are not going to introduce Riemann Zeta's functions in this chapter, but we would be having a dedicated chapter to that function as well. So for that case we need to understand what is actually sum, right? So let's just read this out once. We will start with finite series, later invoke the concept of a limit to extend our formulas to infinite series. Yeah, obviously this will be seen in actions as we focus on telescoping series later in the chapter. To introduce our chapter, we can begin with the definition of summation. So basically this is the definition of summation. So summation is the addition of a sequence of numbers called addends or summands. The result is their sum or total. A series is similar to a sum, yeah, but is often used to refer summation of infinite sequences, right? Okay, so yeah, that's the basic definition, right? We all know that obviously. Okay, and now we have arithmetic and geometric series. You know what, guys, before I just read this stuff out, I would request you to just focus on here what this says. This is an amazing sum which says the sum of first 100 terms of natural numbers, right? So basically this says that if s equals the sum as n goes from 1 to 100 of n. So it does say that it's 1 plus 2 plus 3 plus 4 plus dot 97, 98 plus 99 plus 100, right? Okay. And now, so basically we have to talk about the value of this sum. You know what, guys, I would request you to just find this out. And the most fundamental way, like you can say the most easy way to do this is, yeah, so the most easy way is to just, you just add this up: 1 plus 2, which is 3, plus 3, which is 6, right? But it's gonna take a lot of time, and let me tell you the easiest way that someone did. Well, let's talk about that. Okay. So let's just read this out to get to know that how someone, not someone, but a great mathematician, and I don't want to say him great, but instead I would like to say him the prince of mathematician. Not me. It's not. It's. I'm not the first guy who say that, but a lot of mathematicians considered him as the prince of mathematician, and that is Carl Friedrich Gauss. Okay, so let's just read this out once. We will start by a famous example provided by the story of the German mathematician Carl Friedrich Gauss in his mathematics class. What's that? Okay, not sure. One day, Gauss' teacher asked his class to add together all the numbers from 1 to 100, a task the teacher thought would occupy the students for quite some time. Yeah, obviously. It's time taking when you go through the standard way, which says that you have to add this up. It's 1 plus 2, which is 3, and now 3 plus 3, which is 6, now 6 plus 4, 10. So that's kind of taking time. It's gonna take a lot of time. And at that time there were no calculator, and though even we are having calculator nowadays, but we are not allowed to take them in classes. And that too in that small class, and that too like child's class, kids class. So for that case, yeah. Okay, so he was shocked, like, yeah, he was shocked when young Gauss quickly wrote down the correct answer. Obviously, quickly, guys, just take a look at this word, quickly. How quickly? We'll just take care about that. The teacher could not understand how his student had calculated the sum so quickly, but the 8-year-old Gauss pointed out that the problem was way simpler than the teacher imagined. Whoa, look at the aura. Wow, that's amazing. So, this is the sum, right? Okay, so the way Gauss solved it, look at this down. Many reading this book are familiar with the formula to solve such a problem. Perhaps the background of the aforementioned story as well. We begin by expanding S. So basically, this is S after expanding it, because this sum, as n goes from 1 to n, it's something will be expanded, something like something sort of that, right? And what he did is Gauss started by recognizing that the one pair of the first and the 100th term, the second and the 99th term, and so on, to make a sum of 101. Just take a look at the beauty that he just produced at that time, at a very young age, that is around 8 years of old, 8 years of age. So that's why he's considered as, he used to, and he is, and will considered as the prince of mathematicians. This is gonna be giving us 101. This sum 101, 101, 101. Right. So basically we are having two terms of 100 terms. Like basically we are having 100 terms, right, in the sum. So if we consider, if we are having here too as well, here too. So basically we will be having 50 boxes like this, right? So basically this is your 50 times. So you know what, if every box is gonna give us 101, 101, 101, and 101 and something sort of that, so basically we have 101 50 times. So basically that's going to be giving us 50 into 101, and that is 5050. That's it. Just take a look at the beauty of this. This is really amazing. Now there are 100/2 such equivalent to 101 in S, right? So therefore our answer is S equals 101 times 100/2. So that basically says, and from here we can just take a look at a generalized form which says that this sum as n goes from 1 to k of n is k times k plus 1/2. Right, so basically just take a look at, you can just compare it by your own. So if we consider k equals 100, so let's just consider it for that. So if k equals 100, so we have this sum from n equals 1 to 100 of n. So when if we just plug this back in the formula, so we are having 100 times 100 plus 1/2, which says 100/2 times 101, and that finally says 5050. So yeah, that's how you can just generalize it, and that's how you can prove this down as well. Really amazing, guys. Okay, now let's just talk about this one. So we are having when you expand this out, so it's 2, wait a second, 2 to the naught plus 2 to the 1 plus 2 to the 2, and we have plus 2 to the 3, and that just keeps going up to 2 to the 9 plus 2 to the 10, right? And furthermore we can write 2 to the naught as 1 plus 2 plus 4 plus 8, and it's 2 to the 9. Oh, wait a second, wait a second, let me just write this out as well. It's something sort of that. I don't need to expand this out, I don't want to just write this stuff. Okay, so yeah, here it is written, something sort of that. And now let's just go further. Okay, so we have considered multiplying s by 2, or the common ratio. Okay, so basically we have to, okay, wait a second, just take a look at this. Let's say that it's your a1, this is your a sub 2, this is your a sub 3, and that's just it's going up to a sub 10. Wait, yeah, it's your a sub 10. So just tell me one thing. A sub 2 over a sub 1 is 2, a sub 3 over a sub 2 is 2, a sub 4 over a sub 3 is also 2. So basically this is, wait, it's not infinite. Yeah, so basically this is your common ratio, right? So we have to multiply both sides with common ratio in this equation, in this very equation. So what we get 2s equals 2 plus 4 plus 8 plus dot 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 up to 2 to the 11, right? And now subtracting 2s from s, so basically we were having s equals 1 plus 2 plus 4 plus 8 plus dot 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 2 to the 10, and we are having 2s as 2 plus 4 plus 8 plus 16 plus dot 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 plus 2 to the 11, right? And now what we have to do is subtracting. So yeah, we just have to subtract it down. So we would be having s minus 2s equals, just take a look at this, we just got rid of these 2's, 4's, 8's, 16's, and every term, and what we will be having in the end is 1 minus 2 to the 11, right? And from here it's minus s equals 1 minus 2 to the 11. So from here we can say s equals 2 to the 11 minus 1, and here's the value of that sum, right? So yeah, it's pretty much amazing. Okay, and now let's talk about a general finite geometric sum. And yeah, after looking at you can just think about it. So it's the sum as n goes from 0 to k of r to the n for r should not be equal to 1. Okay, and k is finite. Yeah, so we can apply the same logic from our last example. Okay, so let's just try this out. So we have our s equals the sum as n goes from 0 to k of r to the n. So we can expand this out as 1 plus r squared plus dot 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 all the way up to r to the k. Right, now you can just think of here that we had to multiply with the common ratio. We have to multiply. So if we talk about this, so it's a sub 2, it's your a sub 1, it's your a sub 3, right? And we just keeps going up to a sub k. So just tell me the common ratio. That is a sub 2 over a sub 1, it's r. A sub 3 over a sub 2, it's also r. A sub k over a sub k minus 1, it's r. So basically our common ratio is coming out to be r. So right, so we just have to multiply both sides with r in this equation that we have expanded here. So what we get is r times s equals r plus r squared plus dot 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 all the way up to r to the k plus 1. And again we just have to subtract these two equations. This is the first one and this is the second one. So we would be having s minus r s equals 1 minus r to the k plus 1, because rest of the terms would be just getting rid of with each other. And now we can just factor out as here we have just done that. And now we can just divide both sides with 1 minus r, and here we would be having s equals 1 minus r to the k plus 1 over 1 minus r. So that's literally amazing. Okay, wait, just the condition is that r should not be equal to 1. And now if we just plug that if we replace that condition, that the absolute value of r should be less than 1, and if we try to evaluate the sum up to infinity, that is the way we just we can see here, this is the infinite geometric sum. Okay, so now let's just talk about this. So yeah, we just have to consider that the the absolute value of r should be less than 1, and that's how we can talk about the sum for up to infinity, right? And we will just take care about that, don't worry. But why r should be less than 1, the absolute value of r should be less than 1, we'll get to know. And what if r, the absolute value of r is greater than 1? So basically this sum will not valid, it's diverged. It's gonna diverge. To convert that to a finite number, that's why we need to just have that condition for, yeah. So let's just talk about this. So we have this sum as n goes from 0 to infinity of r to the n, right? And that can be written as limit k tends to infinity, right? And the sum as n goes from 0 to k of r to the n, obviously, because we can just replace that k with infinity, so we can just have that. Okay, and now we know that so far we have successfully derived this as, wait a second, we have done this as 1 minus r to the k plus 1 over 1 minus r, right, in the previous proof. Yeah, here it is. Right, so yeah, it's written over here as well. Okay, and now we know that the absolute value of r is less than 1. So basically it's gonna be 1 over r some types, right? And when r tends to infinity, this is gonna be 0. And basically, and like finally we can say that this part is gonna be 0, right? Just take a look at the absolute value of r is less than 1 as k tends to infinity. Basically it's not r but k tending to infinity. So basically k tending to infinity, so it's r to the k plus 1 is also gonna tend into infinity as well. So r to the k plus 1 is 0, right? So finally we just got rid of that, and finally we are having this sum as n goes from 0 to infinity of r to the n as 1 over 1 minus r, provided that the absolute value of r is less than 1, right? So this is pretty much amazing, I would say. And now it is now a good time to introduce some standard results. The sum of the first n squared is and the sum as n goes from 1 to capital N of small n squared is capital N times n plus 1, capital N plus 1 times 2 capital N plus 1 over 6. Hey, wait. I can see something here which I have done already. Guys, just take a look at this. This is an infinite sum, right? And it's, wait a second, we have geometric 1 over 2 to the n. Yeah, so basically the side length is 1 unit, and we have this sum as n goes from 1 to infinity, right? So basically it's your 1 over 2, right? You know what, I have proved this down, but I'm just gonna get you a summary here. So we have this length as 1 unit, right? So this big length as 1 unit. So if we divide it in half, so wait, where it is? Yeah, okay. So if we divide it in half, so we would be having 1 over 2 here, and again this part is 1 over 2, but again I have divided this part is in half, so it's 1 over 2, and it's 1 over 4, it's 1 over 8, it's 1 over 16, 1 over 32, 1 over 64, and that just keeps going up to infinity. How, I hope you can just understand that, right? Okay. And this is really amazing. This is really amazing, I would say. This is amazingly beautiful, guys. This sum as n goes from 1 to capital N of n cubed is this sum as n goes from 1 to capital N of n whole squared. That is really amazing, guys. And that too equals n squared times the capital N squared times capital N plus 1 whole squared over 4. Yeah, actually both formulas can be easily proved by mathematical induction. Okay, I left an exercise for the reader. Okay, I think I need a separate video to prove this down as well, because I think this is my first time to encounter this, but it's really amazing and I cannot digest it so far. Okay, let's just go further. And now I can see some Bernoulli's number. Wait a second. We have a theorem. The sum as small n equals 1 to capital N of n to the alpha equals 1 over alpha plus 1 times the sum as small n equals 0 to alpha of alpha plus 1 choose n times b sub n, capital B sub n, and that capital B sub n is just Bernoulli's number, times capital N to the alpha plus 1 minus small n. Oh my goodness. And literally this is my first time to encounter this as well. Again, this should be going into my to prove list, the way I have put this one. Yeah, but surely I'll just go for all these things. It's either in this video or my 3 videos that I have done already, where the b sub n denotes the nth Bernoulli number. And now we have the definition of the Bernoulli's numbers. Wait a second. Do you remember, guys? I have used this generating function Basically, this is known as the generating function of Bernoulli's number, and I have done. Okay, so yeah, I have discussed this in detail. Even I have proved, I have calculated what is your b naught, what is your b sub 1, what is your b sub 2, and I think, yeah, with this formula it's the generating function, right? So I would just request you to just watch that video once, and if you want, then I'll just put the comment, put the description, put the link of that video in the description box. And the crazy part is, I have used this generating function to prove this formula down, and you can have a video, just displaying this on my thumbnail, right? So yeah, this is literally amazing. It's a generalized Riemann zeta of even terms, even arguments actually. So it's negative 1 to the n minus 1 times 2 pi to the 2n, and it's b sub 2n over 2 times 2n factorial. Okay, and now we're heading towards our next subtopic, arithmetic geometric series. So basically, it's the combination of arithmetic and geometric series, right? Both of them. And there is some sort of example of that, because this is the sum of n, and it's being multiplied to 4 to the n as well. So that's gonna be basically, this part is, wait a second, this part is your geometric sum, and this part is your arithmetic sum. So yeah, it's a combination of both of these things. Okay, now we have got a chunk of things. We need to just discuss them one by one. So I think this is the greatest result. I'm not sure. Okay, we have, okay, wait a second. Yeah, be defined as an arithmetic geometric progression. Okay, so this is the general form of arithmetic and geometric progression. You know what it is? It's, so basically, this is your common difference, and this is your common ratio to the n minus 1, and this is your generalized the general form of your series progression actually. Yeah, actually, I'm just looking at this very first time, and that's why I just got surprised, because it doesn't mean that I haven't learned, I haven't ever seen these two quantity, these two things, like, you can say, with each other, but this way I have never seen. Okay, so we have capital S sub n equals small n, the sum from small n equals 1 to capital N of a sub n. That can be expanded as, so basically we have to talk about this, and when your n is 1, 2, 3, and that's just equaling up to capital N, a plus b times r plus a plus 2b times r squared plus dot 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 plus a plus capital N minus 1 times b times r to the capital N minus 1. As the nth partial sum, we can express S sub capital N as, okay, wait a second, yeah, I think it's understood. Okay, now we've got a proof as well here. R times capital sub N equals R times, so basically we have to just multiply with the common ratio, right, in this very like sum, right? Okay, and then we just have to subtract it down. So basically, after subtracting it, we would be just having these kind of things, and from here, yeah, it's understood. Yeah, so it's the same stuff that we have did earlier, but yeah, it's kind of, it looks ridiculous at first, but it's all right. Yeah, okay, now we have got another both sums inside a sum, right? So basically this is the curve partial sums. So when you plug n equals 1, so it's 1 over 3, so it's 1 over 3, and it's 2 over 9, right? So basically this point represents 1 over 3, it's 2 over 9, it's 3 over 27, which is 1 over 9. This is your 4 over 3 to the 4th, which is 4 over 81. So that just keeps going up to infinity. Okay, and now we have this thing after expanding it out, and we have a common ratio of 1 over 3, right? So what we have to do is to multiply it with the sum, the way we did here, and now we have to just subtract it down with the s. It's s minus s over 3, and these things would be just yeah. And now we can see some pattern here, that 2 over 3 times s equals 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 87, and that's just going up to infinity. And guess what? It's an infinite geometric sum with a common ratio of 1 over 3. Wait a second. So r is 1 over 3 and a is 1 over 3. So basically it's 1 over 3 over 1 minus 1 over 3, right? So the way we just did here, and finally after just solving it out, we would be having 1 over 2. That means the sum of this part is going to be 1 over 2. The way, this is literally amazing, guys. Actually not 1 over 2, but we have 2 over 3 here as well. So we just have to multiply and divide with 2. Actually multiply with 3 and divide with 2 both sides. So that's going to be giving us s equals 3 over 4. I'm sorry about the 1 over 2. Okay, and now we have this. For r, the absolute value of r is less than 1. If the absolute value of r is capital than or equal to 1, the way, yeah, I did say that this is gonna diverge, right? Okay, yeah, here it is. And now we have chunk of things. Yeah. Okay, so we can just go for yeah. Let's just read this out. This is important. Okay, just wait a second, guys. Just give me a second. Yeah. So to begin, consider the equation for the partial sums of an arithmetic geometric series. So what we have done so far, we are sure with this equation, right? And now we have to take capital N tends to infinity. So this basically we have to talk about when n is at infinity. You capital N actually. Okay. So your s equals limit capital N tends to infinity of s sub n equals limit n tends to infinity of this part, right? And again, provided that the absolute value of r is less than 1. Again, r to the n tends to 0 as n tends to infinity, obviously, because yeah. So for that case, this wait a second. Yeah, this part is gonna be 0. So basically we just got rid of this part, right? And we are having this part as well, r to the, so basically we are having br over 1 minus r whole squared plus a over 1 minus r. That's it, right? So now which can easily be shown. So basically, yeah, we just got this, right? So that was quite easy. That was kind of easy, right? And now as summation by parts, we have s sub capital N equals the sum as n goes from 1 to capital N of a sub n as nth partial sum of this series. We then have not only in the evaluation of series but also in proving convergence and or divergence of series. So yeah, this is amazing. This is important. Okay, let's just talk about the proof. I'm not sure, to be honest. We have we have s sub k to the n as sum from n equals k to capital N of a sub n times b sub n, right? Okay, and now yeah, we know that, we know that, we know that. So your a sub n could be replaced with that. Basically, it says that if s sub n is your nth term, right? I think it's your sum of nth term, right? Yeah, sum of nth term, and s sub n minus 1 is sum of n minus 1th term. So basically s sub n minus s sub n minus 1 is your a sub n. Yeah, I have just learned this in my 10th grade. And now we can just expand this into different sums. Okay. And now we can just expand both of these sums as we can just pull the underlined terms to the outside to obtain. Okay, just wait a second. Okay, actually why I did that, to just combine this one and this one. So we are having s sub capital N times b sub n minus s sub k minus 1 times b sub k, b sub k minus s sub k minus 1 times b sub k. Okay, now that combining the expressions from the second and third line, yeah, so we are gonna be having this much parts combining the terms. Actually, you know what, just take a look at this, just take a look at this, guys. Combining this one with this one with the second one, right? And we have this one with this one, right? So combining those things with each other, we would be having this one, this one, this one, and then that's just, yeah. Okay, and now we can just write this part as a compressed, wait a second, yeah. So we can just write we can just write that down in a summation form as your capital S sub capital N times b sub n minus capital S sub k minus 1 times small b sub k plus the sum as n goes from k to capital N minus 1 of capital S sub small n times b sub n minus b sub n plus 1. And that's how we're done with the proof. Yep, we have got a couple of questions. And we have I think these are some let x be a random variable. Yeah, so I think I should not just talk about this because I'm not sure what it is. So for that case, I'm not gonna just disturb it all. Okay, guys, this book does have a lot of things that I am not quite sure about, and I have just told this thing to you in the very beginning of this series. So please just bear with me. I'm also a learner, right? Yeah. We have telescoping series. Let's just talk about this. A telescoping series is a series whose partial sums only have a fixed number of terms after cancellation. This method of cancelling parts in partial sums is known as the method of differences. For infinite series, one must take the limit of the partial sums. You know what? We were talking about like those the geometric sums, the formula for geometric sums, as we did it for, yeah. Okay, so it was a sub, wait. So it was S equals A over 1 minus R, provided that the absolute value of R is less than 1. So we did found this formula using the telescoping series only. Just take a look at this. Right. Now you can just write this down as the sum as n goes from 1 to infinity as n plus 1 minus n. Right. And we have n plus 1 times n. And now we can just separate the two sums. We have 1 over n minus this sum over n plus 1. So that's going to be giving us your 1 only, I think. So yeah, here it is. That's the telescoping series. We just got rid of the consecutive terms, but since this part is going to infinity, then this whole part is going to be 0, and that's why we have s equals 1. And now we have some sort of Fibonacci sequences here. That is really amazing. These are also some like telescoping series here. Okay, and we have a lot of questions here, so I think I should just pass them all. We have trigonometric series, right? We just got some infinite sums in the argument of trigonometry, right? Okay, now we just have to talk about these formulas, which we can just prove easily, but I'm not gonna just talk about that in this video. So yeah, challenge problems. Wait a second. So he asked us to prove this down. This is really amazing. The sum as small n equals 1 to infinity of arctan of x squared over n squared equals pi over 4 minus arctangent of hyperbolic tangent of pi x over square root of 2 over tangent of pi x over square root of 2. And I will surely make a video on the proof of this one. Surely. This is really amazing. This looks amazing. We have a lot of questions here. Exercise problems. So I think these problems I'm just gonna talk about in some previous next videos, upcoming videos. And now we will be heading towards part 2, that is series and calculus. You know what? So far what we have done is we have talked about differential calculus, right? And then we have talked about integral calculus, and then we just talked about series, simple, though simple. And now what we are going to talk about next, though we have talked about, actually it's not your third, but it's your fourth. So I need to just, yeah, wait a second. Yeah, so basically it's your fourth, and we have talked about the Feynman's trick though. As well. So after combining these three and this one, we are now gonna we will be studying in the next video, that is calculus and sums. That is how you can just take a look at the series and calculus. So yeah, our next video is gonna be amazing, and that's gonna be how we can relate like calculus with series, right? So that's gonna be an interesting video. So yeah, for this video it's enough, guys. And again, guys, if you got to learn something out of it, please make sure to like, subscribe, and share. And if you haven't got a doubt so far, you're free to ask me in the comment section. I'll be there to reply to your questions. Goodbye, guys. Take care. Love you. And just love your life. Enjoy your life. Love each and live each moment, because that's not gonna come back in your life ever again. Goodbye, guys. Love you.